Welcome everyone. Have you ever wondered why your phone stays charged even when it's not plugged in? Or why an incandescent bulb is ready to glow the second you flip a switch? The secret lie in a concept called electric potential energy. Today, our team will break down what this energy is, how we calculate it, and why it is the backbone of our modern world. We'll move on from the simple definition to the complex derivation, and finally, we'll see it in action in real application.
Before we dive into the math, let's get our bearings. Think of a ball at the top of a hill. Because of its position in Earth's gravitational field, it has the potential to roll down and gain speed. In physics, we call this gravitational potential energy. Electric potential energy is very similar. Instead of a ball in a gravity field, we have a charge in an electric field. If you have two positive charges near each other, they want to fly apart. Keeping them close requires work, and that work is stored as electric potential energy.
Wow!
So formally, electric potential energy, denoted as U, is the energy a charge possesses by virtue of its position relative to other charges. It is a scalar quantity measured in joules.
Wait. Electric potential energy is same as electric potential or voltage?
Great question. They are related but different. Electric potential energy, U, is the total energy of a specific charge. Electric potential, or V, or voltage, is the energy per unit charge. V is equals to U over Q. Think of it this way. Voltage is like the height of the hill, while potential energy is how much energy a specific ball has at that height.
To truly understand electric potential energy, we need to see where the formula comes from. Let's look at the work done by the electrostatic force. We start with Coulomb's law, which tells us the force between two charges, wherein force is equals 1 over 4 pi epsilon naught times QQ over R squared. So here, the small q represents at the test charge that we're moving through that field, while the big Q is the source charge, the one creating the field. The distance between their centers is represented by R. To truly understand where electric potential energy comes from, we have to look at the relationship between force and work. Furthermore, we define work U as the integral of force over a distance, because the electrostatic force changes as the distance between charges increases. We can't just use simple multiplication. We must use calculus to sum up every tiny bit of effort the field exerts. If we move our test charge from an initial point R sub 1 to a final point R sub 2, our equation looks like this. By substituting Coulomb's law into this integral, we replace force with the constant K, our two charges Q and the BQ, all over R squared. This integral essentially tracks the energy as the charge moves through the field. By solving this, we find the total change in potential energy, proving that the work done is directly tied to the change in position within that electric field. When we solve this integral, we find that work done by the field is simplified to work equals Q times the quantity of 1 over R sub 1 minus 1 over R sub 2. Now, here is the crucial connection since the change in potential energy is defined as the negative of the work done by a conservative force represented here as delta U equals negative W. We can define the electric potential energy at any specific distance R. By assuming the energy is zero at an infinite distance, we arrive at our core formula U equals KQ over R. This formula tells us something very intuitive about how charges interact. If the charges have the same sign, both positive or both negative, Q is positive, meaning it takes external work to push them together. However, if they have opposite signs, U is negative. This indicates that they naturally want to be together and the system releases energy as they get closer.
Let's put this into practice. Imagine, we have a fixed charge. Q equals positive 5 nanocoulomb at the origin. A second charge Q equals positive 3 nanocoulomb is initially at a distance R sub 1 equals 10 cm. So, how much work does the electric field do? If Q moves to R sub 2 equals 15 centimeters. First, we convert units. 10 centimeter equals 0.10 meters and 15 centimeters equals 0.15 meters. Using our formula, calculating the bracket gives us 10 minus 6.67 equals 3.33. Multiplying it all out, we get a work of approximately 4.5 times 10 raised to negative 7 joules. Because the work is positive, the charge Q gained kinetic energy as it was repelled. Its potential energy decreased by the same amount. It's just like the ball rolling down the hill.
EPE isn't just a textbook concept, it's everywhere. As mentioned earlier, every turn-off appliance in your home is a reservoir of electric potential energy. Number 1. Batteries. In your phone or laptop, chemical reaction keep charges stuck on one side. This creates a potential difference. The charges are bursting with EPE, just waiting for you to press the power button so they can flow and do work. Number 2. Capacitors. These are components in electronics that store EPE directly in an electric field. They are used in camera flashes to release a huge burst of energy instantly. Number 3. Household appliances. Think of a washing machine or an electric stove. When they are off, the stationary charges have potential energy. Once turned on, that energy is converted into kinetic energy to spin the drum or thermal energy to cook your food.
To wrap things up, we've seen that electric potential energy is the stored energy of the electrical world.
It depends on the position and magnitude of the charges.
and it follows a strict mathematical relationship derived from Coulomb's law.
And it obeys the law of conservation of energy, losing potential to gain kinetic or heat energy.
Without it, none of our portable technology or power grids would function.